Okay, our goal is to talk about thermal conduction. I'm on page 72 of volume 3 of the workbook. So let's get right to it. Imagine you have a hot reservoir and a cold reservoir. So for the purposes of this demonstration, you can imagine the hot reservoir would be like a boiling pot of boiling water at some hot temperature, 100 degrees Celsius. And the cold reservoir could be an ice water bath. Another thing it could be is maybe room temp air at T cold equals about 20 degrees Celsius, right? So you could have different types of hot and cold reservoirs, but anyways, they're at some temperatures. And then in there you insert a rod or some slab of material, or could be a cylinder, whatever. The power or rate of energy transfer, or the amount of heat transferred per unit time, is given by this equation. K, which is called thermal conductivity with these weird units, watts per meter per Kelvin, or joule per second per meter per Kelvin, times the temperature gradient, dt dx, the amount the temperature changes per meter. So notice the units do work out, because this is in units of meters squared, this is in units of, say, Kelvin over meters, so we get basically watts or power. Now, to be clear, we're assuming energy is being transferred from hot to cold. It is not impossible to make energy go from a cold reservoir to a hot reservoir. A refrigerator works. We can discuss that in a later chapter. But the natural flow of energy, if you put a metal rod between something hot and something cold, the energy is going to flow from hot to cold. Statistically, there might be a couple of random molecules that go this way, but the overwhelming preponderance are going to go that way. All right? So, and that does come in, that I think that shows up, you're supposed to know that it goes from hot to cold. I think that's obvious, but it does matter in, I think, one solution. Anyways, this is approximately given by this. So this is the exact result, which is valuable if you have to do calculus or like cylinders. That we'll talk about that later. But the approximate result is Ka delta T over delta X. Sometimes we'll just call that the rod length, or sometimes it'll be called a slab. All right, so we usually either use rods or slabs or cylinders for these problems. And so just to give you an idea, if we look on page 69, well, let's get here, let's go to the demonstration really quick. We'll do work problems in a subsequent video. All right, so I've got some boiling water here. I'm gonna pour it in this vessel here. Try not to burn myself. So that's some boiling water. Hopefully you can see the steam. Now I have some different materials. And I know you can't probably see this very well, but this is steel, brass, aluminum, copper. And right now there's thermometers embedded in all these. This is a pretty cool device. And what I'm going to do is I'm going to dip this in the hot water, and you can see which one is going to warm up faster, which one is going to conduct the thermal energy up the thermometers most rapidly. And so if you want, you could pause on page 72 and look at the different values and see, make a prediction. Steel, brass, aluminum, or copper, which one is going to have the temperature go most rapidly? All right, I'm going to do the demonstration. 3, 2, 1. Hopefully you can see this. I'm going to give it a minute. Ooh. Look at that copper and aluminum go. Can you see the copper and aluminum starting to warm up there? I hope that's showing up on the screen. I can't see from here. Whoops. Oh, geez. I just dunked them. Oh, well, whatever. Hopefully you're noticing that the copper is changing color, then the aluminum, and then the brass, and then the steel, which should make sense if you look at their thermal conductivities. Generally speaking, a good electrical conductor, copper or aluminum, is a good thermal conductor. All right, and so we could run this again in ice, and they should cool off more rapidly as well. I don't know if you're going to be able to see this. hard to make good thermal contact with the ice. But the same should happen in reverse, and you get the idea. I'll do a worked example in the next video or something like that.